I would like to welcome Marjan Alirezaie, and she's a professor in the Wallenberg. She's a Wallenberg Autonomous Systems Assistant Professor at the Center for Applied Autonomous Sensor Systems in Örebro University. And she received a PhD in 2015 on semantic perception. And I think we're going to get another really interesting researcher topic. Take it away, Marjan.
Thank you very much. Thanks for the introduction. Good afternoon, everyone. Yes, I am Marjan Alirezaie, and in this session, I am going to talk about neural symbolic systems related to my research line. So I will introduce neural symbolic systems and also talk about like the reason behind their existence. And then in order to actually go to further details, technical details, I will quickly go through 3 different settings of neural symbolic system in the literature. Also 2 existing frameworks related to neural symbolic system, and then I conclude the sessions by listing existing challenges left to address. So I start by repeating the fact that deep neural networks are able to outperform humans in specific tasks, including computer vision, natural language processing, machine translations, and also time series forecasting. So the more specific the task, the better the performance. It is because deep neural networks are more concerned, for the given context, are more concerned with the what aspect. So what is that is planned to be learned, rather than the 2 other aspects related to the context, which is about the transparency of the learning process and also about the reasoning process behind the learning, the how or the why aspect. And because of this feature of the behavior of deep neural networks, it becomes an obstacle for them to tackle other tasks that are actually easy for a human to address. For instance, in the given scene, if you want to enable the machine to answer a question like this, in what order do these cars have the priority? Of course, the very first step is to do the perception, which is like a straightforward for the current state of the art of machine vision to extract entities and traffic signs and marks. However, in order to really come up with an answer for these questions, we require another skill to provide for the machine, which is called as reasoning, whereby reasoning we refer to the process of inferring new facts with the support of given background knowledge. Otherwise, could be almost impossible for a learning process to be able to extract the rules in order to generalize the situation for which it didn't have enough data to learn. So in general, the problems that DNNs are criticized for can be listed into the problem of or the lack of generalization in dealing with previously unseen cases, lack of explainability related to the transparency of the process, and also lack of parsimony, referring to the fact that these DNNs are most of the time data hungry. In order to deal with real-world scenarios, we need to provide 2 different abilities for the machine: the ability to learn from experiences and also the ability to reason from what has been learned. And the current solutions provided or suggested by now or advertised actually is in order to achieve an AI system to be able to reason out of distribution is including self-supervised learning and neural symbolic integration. And I'm going to talk about the second one. So by integration of a logic-based or symbolic machine and neural-based or subsymbolic paradigms, we refer to a combination that provides the ability to deal with the weaknesses of each side, each approach, and at the same time enhance the desired synergy among their strengths. So by symbolic logic, we can actually support the connectionist or subsymbolic networks to use the external knowledge for different purposes, including to enhance the performance or deal with the lack of data. Whereas on the other hand, we can actually use and apply subsymbolic networks in order to deal with the inherent problem with symbolic models, which is about exploring the combinatorial search spaces in a more efficient way. When we are talking about these two paradigms, symbolic and subsymbolic words, we have entities in two different domains of symbolic and subsymbolic that are actually referring to the same concepts in our real world, but in a with a different representation. For example, here we have like the representation of apple in a continuous word, and here the representation of apple in a discrete domain. Of course, although they are different, this representation of different, but with the proper way of combining and integrating this representation, actually we can make them to also be complementary in order to address different problems in real-world scenarios. Now, by going through, as I said, 3 different settings or architecture in the state of the art, we can provide further details related to the integration process. What do we mean exactly by integration? So the first model or the architecture is actually offered and for different application, and it can be known as like a model that allows us to reason upon learning. So for this model, we have like a neural model with the input and output layers. And regardless of the structure that we have for the machine, we consider like continuing the model architecture by applying reasoning, different types of reasoning upon most of the time upon the output layer, but sometimes also the input layer, where this reasoner, of course, is associated with a knowledge model, background knowledge that has been manipulated and constructed by the domain expert. And we use the inference output for different purposes, for example, to refine what we have get from the output or make the output more explainable for the end user. We can actually extend this architecture to find other applications rather than explainability and transparency. For instance, by making this reasoning a bit more complex and providing an interaction line for the end user and the reasoning part, we can actually go one step further and semantically enrich the output that we get from the machine. Related to this model, I can refer to one of our previous work that we were using the satellite imagery data in order to label some features of interest with some rudimentary labels, including, for instance, road, water area, and ground. So in order to use this labeled map for different tasks, such as planning tasks and so on, we were trying to actually apply some sort of reasoning upon what we get from the output layer. The very first types of reasoning was spatial reasoning in order to recognize the existing spatial relations between the regions or segments that we get. And then by associating the process with some ontological knowledge, we were able to actually find more meaningful labels for the regions that we have already labeled through using the machine learning. So for instance, here, based on the relations that we get for this specific area and considering the neighborhood and the spatial relation that it has with its vicinity, we could actually provide another label for this area from road to bridge. It is still a road, but also a bridge, that make it actually useful for different tasks, such as path planning for rescue scenario, for instance. Okay, it works to actually enrich the output of the learning process semantically, but there is these drawbacks that what we are doing is not actual integration here. So the learning is still as before, so it doesn't get familiar with whatever that we were inferring here at the second part. And if we apply it upon another domain, it still works with this initial rudimentary label. But that's why we go to the next model, that we try to close the loop between the learning and reasoning in different way. For instance, related to this model, again, I can refer to the previous work called semantic referee. Again, working with the same data, that here is a big picture of the model. So this bottom part represents the learning module that we had, and we were applying some reasoning module represented on the box on top upon what we get from the output of the learning. And whatever we were inferring back, we were sending it as like kind of feedback as a new channel of data for the learning process. So in this way, we were actually, by relying on this paradigm, we were enabling the learning module to learn about the causes behind its error. And therefore, it was able to enhance the classification accuracy by enabling it to model to learn from its mistakes. So more specifically, what we were trying to do by recognizing some regions that were likely misclassified and considering the neighborhood, for example, here the red part is likely misclassified, but the blue part is labeled as building, and we have information in our ontology by extracting the existing spatial relations and mapping to the concepts that we have in the ontology. We were able to actually find the best possible explanations about this area, which in this case was shadow. So this part, this area was misclassified apparently because it was under the shadow, and that's why the color of this region was changed. So by sending this piece of information, I mean by relabeling the pixels of that region with the new concepts that we inferred, and sending this information back to the learning process, within several iteration steps, we were improving the results. And as we can see, the machine is able to also label other parts of the city with a new concept like shadow. And that's how we were improving the results, by closing the loop between the learning and the reasoning. Yes, again, related to this architecture, we can find different applications. For instance, we can not only learn about the causes behind errors, but just learn new concepts and relations based on what we call weak supervision or distant supervision. We can refer to another work as a joint work in MIT and DeepMind and IBM, actually, based on the Clever dataset. So the task here was to enable machine to actually answer such questions that require reasoning, actually. And the data that we had was just the scene and the question, which is labeled with the final answer as the ground truth. So following the same architecture, here the visual grounding was used, and also the learning parameters was used to learn how to map the given question in natural language to an intermediate representation based on the language, and this is understandable by the existing reasoner, in order to find an answer based on the relation that it gets from the vision part to this question. And that's how, by comparing what it gets from the reasoner and the ground truth, it was able to train the whole system by closing again the loop between the learning and reasoning. So yes, these were like the applications of this domain, we can actually extend this model by separating the existing reasoning part. I'm not going through the details or the differences between the reasoning parts. So what I just want to show here is that this is exactly like the previous paradigm, but as I said, by separating the reasoning part. And these are the applications that we went through, but yes, there is still a problem here, which is about like we still have the human in the loop, and that's why it's not fully automated. We always need to actually provide the knowledge, and this knowledge is, according to this model, is prepared and constructed by the domain expert. And the question is how we can actually make it more automated by excluding the human from the loop, or actually we can rephrase this question by saying that how we can learn to reason or learning the knowledge. We want to exclude the human, and it actually refers to some other works such as structural learning, relation learning, or end-to-end neural symbolic system in the literature. That is one step towards further automation, because we provide less predefined information, and that's how we increase the level of automation for the whole process. So these were like the architectural details, but it will be useful to also go through the details of existing frameworks actually designed for neural symbolic systems. But before that, it's good that we clarify the role of logics in neural symbolic paradigms. So we can actually categorize the role of logic into two parts of logic as constraint or logic as neural program, whereby a constraint here, we mean that what we are trying to do is to enforce certain constraints on a given neural network. Whereas for the second part, we consider the logical representation, and we use this basis to also apply the neural models upon and extend the initial model based on the logic within or during the learning process and so on. But I start with the first role, logic as constraint. Related to that, we can refer to this task, multi-class classification. So here we have such network with multi-class classifications. So in order to make sure that for each instance we have only one output, we can actually apply the logical representation in this format that makes sure that at each step we have either x3, x2, or x1 true. But in order to really be able to integrate this logical constraint, we can actually change the representation, and instead of like providing pure logical form, we go and use the equivalent but probabilistic representations of this constraint. And it becomes the basis for the semantic loss, which is used as like a new parameter to be added to the loss function and make the loss function knowledge aware. So based on some like weight as a learning parameter to be added. So there are many neural symbolic models relying on using logic as constraints on encoding the satisfiability of logical knowledge in the loss function. But the obvious downside here is that by doing so, we are actually losing the ability of reasoning at a pure semantic level, which is actually a very strong feature to use. But here we don't have like the full strength of this pure logical reasoning. So the solution here is come to what we know as one of the framework, deep problog, that use the logical knowledge in addition to neural predicates. So the basic idea in this deep problog framework is, for instance, for like the examples of MNIST data set, yes, the basic idea is to unify the basic concepts in logic, where by this logic we refer to problog, the probabilistic logic language, and the neural network. So what we have as an interface between two different words of symbolic and sub-symbolic part, we use a concept called neural predicate that is equivalent to or related to the neural network. So for instance, here, in order to recognize this handwritten digit into a number 0 to 9, we can actually model this with one rule in probabilistic logic, where we define a predicate that is going to be associated with probability values here, where this probability value is provided by the neural network. So this is the representations of our neural network based on the neural predicate. So this is the image given handwritten digits. This is the number that we are going to predicate, and this is the range of valid value for this prediction. So basically what we can do in the problem is to use neural predicate in order to assign some probabilities to our predicates and facts. So we model the output as probabilistic fact here. And when it's the time of solving, when we want to instantiate the logic program, this predicate actually will be instantiated into set of annotated disjunction. For instance, this given digit is mapped to 0 with this probability. It's mapped to 1 with this probability, to 7 with this probability, and so on, where this probability are what we get from the neural network. And then once we have this probabilistic fact, then we can extend our knowledge and apply reasoning upon it. For instance, one of the tasks is classifying pairs of MNIST digits labeled with their sum. So they are not labeled with their correct number, but we have a pair of handwritten digits, and as I said, the labels is equivalent to the sum of these two digits. So the benefit of deep problem after representing the neural predicate is to encode the addition in logic. So we want to see how, by knowing how to add, how we can actually help the learning process to recognize these digits. So the learning of these digits becomes an intermediate representation that, by closing the loop between learning and reasoning, we are trying to address this problem. So this is the representations of our predicate, and that's how we are actually using them in order to introduce a new concept, addition of these two images to Z, and that's how we are going to actually provide the reasoning behind this addition operator. So this relies on N1 and 2, which are the values that we get from the neural networks, and that's how, by knowing the expected value here that we have, we are sending feedback to the learning part in order to improve the learning process, which is about recognizing the digits individually. So as long as it's about single digit number, it works. And actually the state of the art in deep learning also they have no problem in addressing this problem. So as we can see, the accuracy of both deep problem and CNN are almost at the same level. But what if we want to actually extend the numbers, the digits, and want to learn how we can actually learn the additions when we have more than one digits for each number? So the question is that how we have to extend the CNN. Of course, for like the concatenations of both images, we need to change the dimensions of our classes from 10 to 19. But the good part, or the benefit of applying deep problem, is that we don't need to actually change any settings in the neural part. We just need to define new predicate or extend our predicates in the logic part in order to handle numbers with more than one digits. So the accuracy of deep problem doesn't change, almost at the same level without even requiring to change the settings in the neural part. So it comes from the fact that we provide an interface here without actually being needing to manipulate the structure of each side. So just quickly speaking about like the integration here, the semantic parts are described in terms of parametric circuits, and these arithmetic circuits are differentiable, and because of that, the integrations of the information that we have in this domain with the neural part becomes just straightforward and easy. So yes, knowing all of these applications of existing neural symbolic models, the message that we can have about like neural symbolic systems, where and how we can use them actually depends on the models of neural symbolics and different types of like the way that they use the logic and so on defines and indicate the types of challenges that we need to address. So for instance, lack of ability to reason at the pure logical level is one of the problems that we have in one of the models. Or if we want to consider the pure logical level, then we have to deal with the scalability issues related to these combinatorial spaces and so on. And one of the research question here is that how we can actually do the trade-off. But yes, obviously they are promising approaches as long as we know that we have knowledge about the domain, but not enough data for the neural learning process. And we can find applications of neural symbolic systems, for instance, in robotics, when we need to do perception under uncertainty, or we need to deal with the compositional generalizations in different domains, such as linguistic, when we are going to develop conversational agents, or in vision, or let's say wherever that we require to do long-term autonomy or achieve long-term autonomy for intelligent systems in real-world scenarios. So thank you very much. And I would like to also thank Professor Luc de Wright as a guest, VASP guest professor at Örebro University, that part of the slides were actually inspired from the research bundle, his group in Leuven.
Yeah, thank you very much.
Thanks.
We ran a bit over time, but I saw that there were not that many questions. I figured it would be good to finish your talk, and it's very interesting. I have one question which actually came from Alirezaie. Could we use this approach to transfer knowledge for a new task?
For the new task, by new task, you mean when, for example, we want to apply the model, the developed model, for a completely different scenario, or yeah, the situations that we haven't seen, or
I'm afraid you'll have to interpret it since Sahara is already in the next session and I'm still here.
yes. So what is here? I mean, one of the idea or assumptions behind neural symbolic system is that we need to provide the knowledge related to the context. So as long as the knowledge is generic enough to address or cover two different situations or domain, we can say that the knowledge is maybe enough. But if we need to add more specific situations about the new domain, then we need to also add it and modify the knowledge part to enable the reasoner to use these changes or specific situations, about the specific situations.
Mm-hmm. Understood. Marjan, thank you very much. It was very interesting.
Thank you.
I really appreciate it.